Dear students, I am Pei Zhang from Tianjin University, IEEE Fellow. The title of this course is Application of Reinforcement Learning into Power System Operation. I use power system operation as the engineering background because it contains the exact features that make reinforcement learning valuable: high-dimensional states, uncertain disturbances, time-coupled decisions, and hard security limits. A power grid operator is never choosing an action in isolation. A switching action, a load transfer action, a generator tripping action, or a dispatch adjustment changes the future condition of the network. The learning agent must therefore connect observation, action, feedback, and long-term performance. The cover also indicates the course setting. The topic comes from power system research at Tianjin University, with applications across restoration, emergency control, economic dispatch, and broader operational optimization. My purpose is to explain not only what the algorithms are, but why the physical constraints of power systems shape the state, action, and reward design. The course follows 5 parts. The first part builds the reinforcement learning foundation: Markov decision processes, value functions, policy optimization, and deep reinforcement learning algorithms. The second part moves to distribution system restoration, where an operator must restore load after a fault while respecting voltage, current, topology, and switching constraints. The third part studies emergency control, especially transient stability control after severe disturbances, where the system has only a short response window. The fourth part studies economic dispatch, where the problem is not a single emergency action, but a continuous operating policy over time. The final part summarizes technical innovations and research outputs. I connect the 4 application areas through one common logic. A power system operation problem becomes a sequential decision problem when the current state is measured, an action is selected, the grid evolves, and a reward evaluates whether the action improves security, economy, or restoration. The details change across applications, but the modeling chain is the same. Reinforcement learning is presented as an agent interacting with an environment. The agent observes a state, selects an action, receives reward or penalty, and then observes the next state. In power systems, the environment is not an abstract game board. It is a physical grid with network constraints, device limits, protection actions, and operator objectives. Constant trial and error means that the learning process must explore many operating scenarios, but exploration is normally placed in simulation rather than in the real grid. Long-term return is essential because a locally attractive action may create later overloads, voltage violations, or restoration dead ends. The agent environment diagram captures this closed loop. The references to stochastic optimization matter because many grid operation tasks are sequential stochastic optimization problems. Renewable output, load, faults, and communication delay introduce uncertainty. Reinforcement learning gives a practical computational route when the state space is too large, the model is incomplete, or a real-time decision must be obtained faster than a full optimization can be solved. I also treat reward design as an engineering contract. If the reward ignores security, the learned behavior will ignore security. If the state omits the variable that reveals risk, the agent cannot invent that knowledge. Good reinforcement learning begins with good operational modeling. The Markov property is the first mathematical condition behind the course. A state is Markovian when the probability distribution of the next state depends on the current state and not on the full history. In power system terms, this means that the selected state variables must contain enough information to predict the relevant future evolution after an action. If generator rotor angles, speeds, bus voltages, switch positions, and loading conditions are missing, the learning model may appear to be Markovian mathematically but fail physically. The small state transition diagram and matrix illustrate how probabilities connect present states to future states. A transition probability of 0 means the move is impossible or not observed. A larger value means that transition is more likely. For grid operation, the Markov assumption is useful but also demanding. The engineer must decide which measurements make the state sufficiently informative. Wide area measurements, supervisory control data, and simulation states can help convert a dynamic grid into a usable Markov decision process. A Markov decision process adds actions and rewards to the Markov process. The tuple contains the finite state set, the finite action set, the transition probability matrix, the reward function, and the discount factor. In power system operation, the state set may include voltages, flows, generation outputs, topology, and stability indicators. The action set may include switch operations, generator redispatch, load shedding, reactive power adjustment, or emergency tripping. The transition probability connects the selected action with the next operating condition. Because the same action can have different consequences under different loading, renewable output, or fault conditions, the transition is not simply deterministic in many practical settings. The reward function translates engineering objectives into a scalar signal. A policy maps a state into a distribution over actions. Deterministic policies choose one action with certainty. Stochastic policies preserve exploration or model uncertainty. The discount factor controls how much future reward is valued. For dispatch and restoration, future consequences are central, so discounting cannot be treated as a minor parameter. Cumulative reward measures the total consequence of a sequence of decisions. The return is written as the immediate reward plus discounted future rewards. The discount factor gamma decides how strongly later outcomes influence the present decision. In a restoration problem, a switching action that restores a small load immediately may block a later path to restore a larger load. The value function should capture that delayed cost. The state value function is the expected return when the system starts from a state and follows a policy. The state action value function, commonly called the Q function, is the expected return when the agent takes a specific action in a specific state and then follows the policy. These value functions are the bridge between operational judgment and algorithmic learning. They tell the agent that an action is not good merely because it produces a positive immediate signal. It is good when its expected future trajectory improves security, economy, or recovery. That is why value estimation becomes central in DQN and related algorithms. The algorithm classification separates value-based methods and policy-based methods. Value-based reinforcement learning estimates the value of actions and then selects the action with the best value. DQN, double DQN, and dueling DQN belong to this family, and they are especially useful when the action space is discrete. Many power system control actions are discrete or can be discretized, such as opening a switch, closing a tie switch, selecting a generator tripping level, or choosing a load shedding block. Policy-based reinforcement learning directly parameterizes the action policy. Policy gradient, actor-critic, PPO, and DDPG belong to this second family. They are attractive when the action space is continuous or when direct policy improvement is more stable than value maximization. Power system applications often require a hybrid view. Restoration and emergency action selection may favor value-based algorithms, while dispatch and continuous control may favor actor-critic or PPO structures. The algorithm family should match the physical action space, not just the popularity of the method. I also pay attention to observability. A discrete action problem can still fail if the state does not capture topology or dynamic stability. A continuous policy can still fail if action bounds are not enforced. Algorithm selection and engineering modeling must be decided together. DQN extends Q-learning by replacing a table of state action values with a neural network. Traditional Q-learning updates a value estimate using the current reward and the maximum future Q value. That update works for small state spaces, but a power grid state may contain many bus voltages, generator outputs, line flows, and topology indicators. A table would explode in size. The neural network approximates the Q function by learning a mapping from state features to values for candidate actions. The network diagram indicates how the state enters the model, passes through hidden layers, and produces Q values for multiple actions. The engineering interpretation is direct. For a measured grid condition, the model estimates the long-term benefit of each available action and the controller selects the action with the highest estimated value subject to feasibility. DQN therefore converts a high-dimensional operating condition into an action ranking. The quality of that ranking depends on realistic simulation data, meaningful reward signals, and careful treatment of unstable or unsafe actions. Double DQN addresses the overestimation problem in standard DQN. In standard Q learning, the same value function can both select the best next action and evaluate that action. Random errors then tend to be amplified because the maximum operator prefers overestimated actions. Double Q learning separates action selection from action evaluation. One network chooses the next action and the other network evaluates the value of that chosen action. The diagram shows an updating action branch and an updating evaluation branch. In power system operation, overestimation is not just a numerical inconvenience. If a controller overestimates the benefit of a load transfer path or an emergency control action, it may select a strategy that appears secure in training but fails under actual constraints. Double DQN reduces that risk by making the target value less biased. It is especially useful when the reward surface is noisy, the disturbance set is diverse, or the action values are close. These are common conditions in grid restoration and emergency control. Dueling DQN separates the value of the state from the advantage of each action. The value stream estimates how favorable the current state is regardless of the chosen action. The advantage stream estimates how much better or worse a specific action is compared with the average action under that state. The two streams are combined into the final Q value. The neural network diagram shows the split before the output layer. This design is useful in power systems because some operating states are already clearly good or clearly bad. When a feeder is lightly loaded and voltage is normal, many actions may have similar value. When the system is close to instability, a few actions may become decisive. Dueling DQN helps the model distinguish the background quality of the state from the extra contribution of each action. That improves learning efficiency when many actions have similar effects in normal conditions, but different effects near constraints. The method is therefore well suited to decision tasks with sparse critical moments. Policy gradient methods optimize the policy directly. Instead of estimating a Q value for each action and then taking the largest one, the policy itself is represented by parameters, and those parameters are updated in the direction that improves expected return. The equations show the objective gradient with respect to policy parameters. The probability of taking an action under the current policy appears inside the gradient, so actions that produce better returns become more likely. This approach is powerful when actions are continuous or when the policy must represent a probability distribution. The cost is sample efficiency. A pure policy gradient method often relies on Monte Carlo trajectories, which means the network parameters may be updated only after a complete episode. For power system simulation, that can be expensive because each episode may require power flow, dynamic simulation, or time series dispatch calculation. Policy gradient methods therefore need variance reduction, baseline functions, or actor-critic structures when applied to realistic grid problems. The benefit is direct policy control. The burden is computational efficiency. Actor-critic combines policy-based and value-based learning. The actor network chooses actions, and the critic network evaluates the quality of those actions. Both networks receive state information. The actor produces the policy, while the critic estimates a value signal such as V of S or Q of S and A. The temporal difference error compares the observed reward plus discounted next state value against the current value estimate. That error becomes a learning signal at each step, so the algorithm does not need to wait for a full Monte Carlo episode before updating. In power system operation, this matters because a single episode may be a restoration sequence, an emergency transient, or a day-ahead dispatch trajectory. Step-by-step learning makes better use of simulation data. The actor-critic diagram also clarifies the division of labor. The actor is responsible for feasible control, and the critic is responsible for judgment. If the critic is poorly designed, the actor may learn attractive but unsafe actions. Reward engineering and constraint handling remain essential. PPO improves policy gradient learning by limiting how much the policy changes at each update. The probability ratio compares the probability of an action under the current policy with the probability under the old policy. The clipped objective prevents that ratio from moving too far away from 1. This is not a cosmetic mathematical detail. In a power system operation task, a large policy update can suddenly move the controller from conservative to unsafe behavior, especially when the training samples are limited or concentrated around a few scenarios. Important sampling allows data collected under an old policy to be reused for updating a new policy, but reuse becomes dangerous if the new policy deviates too much. The clipping mechanism keeps learning stable while preserving improvement. PPO is therefore attractive for dispatch and continuous control problems where the state and action spaces are large and the policy must evolve smoothly. The method balances sample reuse, stability, and computational simplicity, which explains its wide use in modern reinforcement learning applications. DDPG is designed for continuous action spaces. The actor network receives the state and outputs a deterministic continuous action. The critic network evaluates the state-action pair by estimating Q value. The critic is trained using a Bellman target, and the actor is updated in the direction that increases the critic's evaluation. Target networks and soft updates stabilize the training process. In power system applications, continuous actions appear in generation set points, voltage control, reactive power control, and dispatch adjustments. A discrete action list can become too coarse, while a continuous policy can represent fine operating decisions. The diagram shows the actor producing an action and the critic judging it. That structure is powerful but sensitive. If the critic learns an inaccurate value surface, the actor may exploit errors. In engineering use, DDPG therefore requires realistic constraints, action bounds, and validation against power flow or dynamic simulation. It is a useful tool when the control variable is naturally continuous rather than a switching decision. The second part applies reinforcement learning to distribution system restoration. The outline highlights a shift from algorithm principles to an operational problem. Restoration is a strong example because it is sequential, constrained, and time-sensitive. After a fault isolates part of a distribution network, the operator must decide which switches to open or close, which load can be transferred, and how to avoid violating voltage or line current limits. A single switching action changes network topology, so the feasible action set and the system state change after every decision. That is exactly the pattern of a Markov decision process. I treat the restoration problem as a learning task only after the engineering quantities are clear: topology, switch status, lost load, branch current, bus voltage, and restoration objective. Reinforcement learning should not replace physical feasibility checks, it should learn from them. The agent receives reward when it restores load efficiently and penalty when the action causes overload, voltage violation, excessive switching, or islanding risk. A distribution network is often designed with closed-loop capability but operated in open-loop mode. That means alternative paths exist physically, but the normal operating topology avoids loops for protection and operation reasons. When a fault causes load loss, the distribution system operator searches for a route to pick up the lost load through switch operations. The diagram maps the problem into an environment and an agent. The environment contains the distribution network, voltage status, current status, line status, fault status, and constraints such as voltage limits, line capacity, radial operation, and effective operation. The objective includes restoring load, reducing switching actions, improving voltage quality, and reducing losses. The flow on the right shows the agent obtaining a state, evaluating Q value, selecting an action, executing it, observing the updated state and reward, and then improving the review value. This is not abstract trial and error, it is a digital rehearsal of operating decisions under constraints. The learning process converts many simulated restoration attempts into a policy that can rank feasible switching actions. I regard every switch as both a control device and a topology modifier. After one switch changes status, currents, voltages, losses, and feasible later actions all change. That is why restoration is a sequence, not a one-step classification problem. The restoration reward combines long-term and short-term incentives. The long-term incentive is cumulative load recovery divided by the accumulated number of actions. That ratio encourages the agent to restore more load with fewer switching operations. The short-term incentives include voltage overrun penalty, current overrun penalty, tie switch imbalance penalty, and non-radial penalty. These penalties are essential because load recovery alone can push the agent toward unsafe topologies. The diagram also shows real-time state being obtained from the distribution grid, the calculation of evaluation value and state change, and the neural network updating value estimates for decision optimization. From an engineering perspective, the reward function is the operating philosophy written in mathematical form. High load recovery is good, but not if it overloads feeders, violates voltage limits, creates non-radial operation, or uses too many switching actions. The agent learns the trade-off only if the reward function contains those trade-offs. Poor reward design would create a controller that is fast but operationally unacceptable. The improved DQN structure uses experience replay and target network freezing. The estimation network produces Q values for possible actions in the current state. The target network estimates the maximum Q value for the next predicted state. The loss function compares the current network estimate with a target built from reward and future value. Experience replay stores past transitions, then samples them for training. That breaks the strong correlation of consecutive restoration steps. Without replay, the network may overfit to one restoration trajectory or one fault scenario. Target network freezing improves stability because the target value does not chase the rapidly changing estimation network at every step. For distribution restoration, these two mechanisms are practical. Training data come from many switch operations, faults, load levels, and topology states. Replay lets the agent revisit rare but important cases. The target network gives a steadier learning signal. The result is a controller that can learn restoration logic from a complex simulation environment while avoiding unstable value updates. OpenDSS provides the distribution network simulation environment. It can calculate three-phase distribution power flow and expose a COM interface for programming languages such as Python. The workflow on the page uses Python to call the OpenDSS interface, build the simulation training environment, simulate manual switch operations, and read real-time quantities such as voltage, current, and phase angle. The SCADA system records phase angle, current limits, operation counts, load shedding, line losses, and network islanding. These records are needed to judge whether a selected action is feasible and valuable. The important engineering point is that reinforcement learning requires a simulator that can evaluate consequences. The agent does not merely classify a network state, it acts, the simulation updates the network, and the reward reflects physical and operational outcomes. By coupling Python with OpenDSS, the training environment can generate many restoration scenarios safely. This reduces dependence on handwritten restoration rules and allows the policy to discover efficient switching sequences under realistic constraints. The training curve shows reward increasing as the number of training sessions grows. Early in training, the curve is noisy because the agent explores many poor actions. It may choose switch operations that restore little load, violate voltage limits, or create excessive losses. As training continues, the agent receives repeated feedback and begins to select better actions. The reward stabilizes at a higher level, which indicates that the policy has learned useful restoration behavior. The curve should be interpreted carefully. A rising reward is necessary but not sufficient. It must be checked against engineering indicators, load recovery percentage, number of switching actions, voltage violations, line overloads, and restoration time. In a power system setting, a high reward curve is meaningful only when the reward was designed to reflect operational constraints. The value of this result is that the trained agent can choose restoration actions rapidly after a new fault, reducing the time spent searching through many feasible topologies manually or through slow combinatorial optimization. The two charts compare how training affects restoration behavior. The left chart shows that the number of switching actions decreases while the percentage of recovered load increases. This is the desired direction. The agent learns to restore more service with fewer operations. Fewer switching actions mean lower operational burden, less equipment stress, and fewer opportunities for incorrect switching. The right chart connects successful restoration count with loss percentage. As successful cases accumulate, loss behavior becomes more controlled. The curves are not simply performance decoration, they show whether the learned policy is moving toward an operator's practical objective. In restoration, restoring all possible load is not the only target. The operator also cares about losses, voltage quality, radiality, and action count. These curves indicate that the learned policy is discovering more efficient restoration sequences. The paper citation at the bottom anchors the result in a published distribution network restoration study, linking the algorithm design with a real power engineering research problem. The comparison table reports switching actions, load loss, network loss value, and computation time for different methods. The improved DQN with experience replay and target network freezing restores the load with zero load loss in the listed case and has competitive network loss. Traditional DQN has fewer switching actions in one case but leaves load loss, which is not acceptable when service restoration is the dominant objective. The heuristic hybrid algorithm can also recover load, but the computation time is longer than reinforcement learning. The lower table is important for engineering deployment. A method that produces a good restoration plan too slowly may not support real-time operation. Reinforcement learning shifts the heavy exploration into offline training, so online decision time can be very short. The table also reminds us that algorithm quality is multidimensional. The best method must balance load recovery, losses, action count, and response speed. Reinforcement learning is valuable when it improves the online decision speed without sacrificing feasibility. The diagram extends restoration from a basic DQN setting to graph-based reinforcement learning. A distribution network is naturally a graph. Buses are nodes, lines and switches are edges, and electrical quantities live on both nodes and branches. The figure shows state switching, graph data extraction, graph convolution, and a queue network or target network. This structure is more faithful to the topology than a flat vector representation. When topology changes after a switch operation, the graph representation can update the relationship among buses and branches. That is important because restoration is fundamentally a topology problem. A graph convolutional network can aggregate local neighborhood information, such as nearby voltage conditions and feeder loading, before the reinforcement learning agent selects an action. The engineering value is better generalization. A policy trained on one topology may adapt more naturally to change network structures when the model understands graph relationships. This is why graph reinforcement learning becomes attractive for modern distribution automation with many switches and distributed resources. I also emphasize that graph features are not only mathematical convenience, they preserve adjacency, electrical distance, and feeder structure. Those relationships strongly affect whether a load transfer path is safe after a contingency. The table compares literature strategies and a graph reinforcement learning method. The columns include whether distributed generation is included, load recovery rate, number of actions, and the decision time. The traditional literature methods can reach high recovery percentages, but some require longer decision time or do not include distributed generation. The graph reinforcement learning method achieves high recovery with a small number of actions and a short decision time. The main engineering message is not that one table proves universal superiority, it shows the direction of progress. As distribution networks include more photovoltaic generation, energy storage, controllable loads, and automated switches, restoration decisions become more complex. A rule-based method may require many special cases. A learning method can absorb more operating scenarios during training, but it must still be verified against radiality, voltage, current, and protection constraints. The comparison supports the argument that reinforcement learning can be a decision support tool for restoration, especially when fast response and topology adaptability are required. The topology change example tests whether the learned method can still perform when the network structure changes. The upper diagrams show the distribution network before and after topology modification. The table reports average load recovery percentages under different scenarios and methods. Before topology change, DRL and graph reinforcement learning achieve high recovery. After topology change, performance drops, which is expected because the operating structure has changed. The graph reinforcement learning method remains more robust because it uses graph information rather than relying only on a fixed feature vector. The topology and node change scenario is the hardest case, and the recovery percentage becomes lower. This result is valuable because real distribution systems are not static. Switch maintenance, feeder reconfiguration, new distributed generation, and load growth all change the network over time. A practical learning-based restoration method must generalize beyond the exact topology seen in training. Graph awareness and scenario diversity during training are two ways to improve that generalization. The third part studies emergency control. The outline marks the shift from distribution restoration to transient stability control. Restoration usually follows a fault after the affected area has been isolated, and the objective is to recover service. Emergency control operates during or immediately after a severe disturbance when the grid may be moving toward instability. The action window can be very short. Generator tripping, load shedding, fast switching, or other corrective actions must be selected based on real-time measurements and system status. This application is more dynamic than distribution restoration because rotor angle, frequency, voltage, and power flow trajectories evolve over seconds or even less. Reinforcement learning is attractive because it can learn a mapping from disturbance states to emergency actions offline, then produce an online decision quickly. The challenge is much stricter safety. Exploration must remain in simulation. Reward design must reflect stability and control cost, and the final policy must be validated on dynamic cases that include timing uncertainty and severe faults. Emergency control includes generator tripping and load shedding used to maintain system stability under fault disturbances. The bullets emphasize that emergency control should be real-time and based on real-time measurements. Many existing controls are open-loop schemes triggered automatically after a contingency. Such schemes are simple and fast, but they may be conservative or poorly matched to the actual operating state. Past research often formulates emergency control as an optimization problem. The advantage is accuracy and expansibility. The disadvantage is computation burden. A detailed optimization can be too slow for real-time control, especially if it contains AC power flow, dynamic stability constraints, and mixed discrete continuous actions. The two diagrams show the practical control chain: data acquisition, analysis, control, decision, and execution. Machine learning enters because it can learn the relationship between measured states and good actions before the event occurs. During online operation, the learned policy can produce a fast candidate action, while engineering checks can verify feasibility before execution. The emergency control optimization model is transformed into a reinforcement learning model. On the optimal control side, the objective minimizes control cost, including generator tripping amount and load shedding amount. The constraints include generator output limits, load limits, voltage limits, and the rotor angle stability constraints. On the reinforcement learning side, the state space includes generator rotor angles, rotor speeds, bus voltage magnitudes, and voltage phase angles. The action space includes generator tripping and load shedding quantities. The reward function is separated into long-term and short-term terms. The long-term reward uses whether the system becomes stable. The short-term reward uses control cost, constraint violation, and intermediate physical indicators. This mapping is the core modeling step. The agent must observe enough dynamic information to judge stability, choose only actions that can be executed, and receive a reward that punishes both instability and excessive control. The method succeeds only when the reinforcement learning variables correspond to real emergency control levers. The formulation also shows a necessary discipline. The agent is not allowed to create arbitrary actions. Generator tripping and load shedding have physical limits, operational cost, and protection implications. The action space must respect those limits before learning begins. The reward function combines a transient stability index with several short-term penalties. The long-term reward uses TSI to decide whether the system is stable. TSI compares the maximum rotor angle separation with a reference angle, so a larger separation indicates that generators are moving away from synchronism. Short-term reward includes an energy function-based term, control cost, control step penalty, generator capacity violation, and voltage violation. This design reflects engineering priorities. Stability is the first requirement. If the system remains unstable, a low-cost action is not acceptable. But among stabilizing actions, the controller should prefer smaller generator tripping, smaller load shedding, fewer steps, and fewer operating violations. The energy function reward gives the agent a physical signal before the final stable or unstable outcome is fully observed. That can improve learning because the agent does not wait until the end of a dynamic trajectory to receive all feedback. The reward function therefore connects transient stability physics with reinforcement learning optimization. I also view the penalty terms as guardrails. They prevent the agent from stabilizing the system by creating a different operating problem, such as severe voltage violation or excessive generation removal. A usable emergency policy must recover synchronism and preserve acceptable operation. The DQN process for emergency control includes an evaluation network, a target network, delayed updates, temporal difference error, and backpropagation. The evaluation network estimates Q values for candidate emergency actions under the current state. The target network generates a more stable target using the next state and the maximum future Q value. The temporal difference error is the gap between the target and the current evaluation. Backpropagation adjusts the evaluation network to reduce that gap. In emergency control, the candidate actions may include different generator tripping or load shedding strategies. The input state may contain dynamic measurements after a fault. The delayed update mechanism matters because dynamic simulation data are noisy and highly scenario dependent. If both networks change too quickly, the training target becomes unstable. A stable DQN training process allows the policy to learn which actions tend to stabilize the system under severe disturbances while avoiding unnecessarily large control effort. The diagram is therefore a decision pipeline, not just a neural network picture. The case study uses the New England test system with 39 buses, 10 generators, and 19 loads. The state space dimension is 98, which reflects the multiple dynamic and electrical variables needed for emergency control. The evaluation network and target network have similar multi-layer structures. The reward function parameters appear in the table, including positive and negative stability rewards and weights for control cost, load shedding, voltage, energy, and steps. These numbers are not arbitrary decorations. They encode the trade-off between stabilizing the system and limiting the amount of corrective action. A large positive reward for stable recovery encourages the agent to prioritize transient stability. Penalties for control cost and violations prevent extreme actions. The case is appropriate because the New England system is a standard benchmark for stability studies, and it is complex enough to test whether the learned policy handles multi-machine dynamics. The example connects the algorithm design to a recognizable power system simulation environment. I used the benchmark to separate two questions. First, can the network learn a stable policy under repeated faults? Second, does the learned action still make engineering sense when the rotor angle trajectory and control amount are inspected? The disturbance case applies a three-phase fault at the beginning of line 16 to 17 for 0.1 seconds, followed by line tripping. Time delay uncertainty is modeled as a normal distribution with mean 100 milliseconds and standard deviation 20 milliseconds. The training curve shows that reward gradually increases and then approaches a stable high level after many episodes. This case is important because emergency control is affected by measurement delay, communication delay, computation delay, and actuator delay. A policy trained only under a fixed delay may perform poorly when the actual delay changes. The reward curve indicates that the agent can learn a useful action policy even when timing is uncertain. The vertical variation during training reflects exploration and scenario variability. For engineering deployment, delay modeling is essential. A control action that would be stabilizing at one instant may become insufficient if executed too late. Reinforcement learning can incorporate this uncertainty during simulation so that the online policy becomes more robust to realistic control timing. The curves compare generator rotor angle trajectories before and after emergency control. Without effective control, rotor angles separate and the system moves toward loss of synchronism. With control, the relative angles settle into a more acceptable range. The table reports a two-step control sequence. The first step sheds load at bus 28, but the TSI criterion remains below zero, indicating instability. The second step trips generator 34, after which TSI becomes greater than zero and the reward becomes strongly positive. This result illustrates sequential decision-making. The first action improves the condition but does not fully stabilize the system. The second action completes the recovery, although it has a larger physical impact. A good emergency controller must know when a mild action is insufficient and when a stronger action is justified. The value of reinforcement learning is that it can evaluate the expected consequence of a sequence, not only a single static control move. The curves provide the physical validation of the learned action sequence. Rainbow integrates several improvements to DQN, double DQN, prioritized experience replay, dueling network, multi-step learning, distributional reinforcement learning, and noisy DQN. The first formula describes prioritized replay, where transitions are sampled with probability related to the absolute temporal difference error. Samples that the model currently finds surprising or difficult receive higher probability. This improves learning efficiency because rare but informative disturbances are revisited more often. Multi-step learning uses rewards over several future steps rather than only one-step targets. For transient stability control, multi-step information is valuable because the effect of an emergency action is not always visible immediately. A generator tripping action may reduce acceleration and improve angle separation after a short dynamic interval. The loss function shown for multi-step DQN trains the network to match a target built from these longer returns. Rainbow is therefore not a new physical model, it is a stronger learning architecture that can improve convergence and robustness for emergency decision-making. Distributional reinforcement learning estimates the distribution of returns rather than only the expected return. The return distribution is approximated over a fixed support of atoms, and the learning objective minimizes divergence between the current distribution and the target distribution. In power system emergency control, this is meaningful because the same action can have different outcomes under different fault clearing times, load levels, renewable output, or delay realizations. An expected value alone may hide the risk of severe failure. A distributional view can distinguish between an action with moderate but reliable returns and an action with high average return but large downside risk. The equations define the support points and the target distribution update. The engineering value is risk awareness. Operators care about worst-case or low-probability severe outcomes, not just average reward. Distributional reinforcement learning gives the agent richer information about uncertainty in returns, which can be valuable when choosing emergency control actions under uncertain dynamic conditions. Noisy DQN adds trainable noise to network parameters. The formula shows a linear transformation with deterministic weights and bias plus noisy components. The random variables are combined element by element with learned noise parameters. This approach replaces simple random exploration with structured exploration inside the network. In power system emergency control, noisy measurements are unavoidable. PMU data, communication channels, and state estimation can all introduce measurement noise. The text notes that over time the neural network can learn to ignore the noisy stream, helping the agent generate correct control actions without being affected by PMU measurement noise. The phrase should be understood carefully. The algorithm does not make the physical measurements perfect. It trains the policy to be less sensitive to irrelevant random perturbations and more attentive to stable patterns in the state. For emergency control, this is valuable because the action must remain reliable even when measurements are imperfect and the control window is short. The four training curves compare DQN, double DQN, dueling DQN, and rainbow under the same fault. The red circles highlight convergence regions. Standard DQN improves but shows more fluctuation and slower stabilization. Double DQN reduces overestimation but still has noticeable variation. Dueling DQN converges more cleanly because it separates state value from action advantage. Rainbow achieves the best convergence in the comparison, reaching a high reward region more rapidly and with better stability. The practical meaning is that algorithmic refinements change the reliability of the learned controller. In emergency control, convergence is not only a training convenience. Poor convergence can mean that the final policy is sensitive to random initialization, scenario selection, or measurement noise. Better convergence indicates that the policy consistently discovers effective stabilizing actions across repeated training. The comparison supports the use of integrated DQN improvements when the control problem is high risk, dynamic, and influenced by uncertainty. I would still validate the final policy on unseen faults. A clean training curve is encouraging, but grid operation requires out-of-sample testing, stress cases, and confirmation that the selected control action is physically interpretable. The fourth part applies reinforcement learning to economic dispatch. The outline separates this topic from restoration and emergency control because the time scale and action type are different. Restoration and emergency control focus on abnormal conditions after faults. Economic dispatch operates continuously or repeatedly under normal operating constraints. The objective is to meet demand at lower cost while respecting generator limits, ramping limits, voltage limits, line flow limits, reserve requirements, and uncertainty from renewable generation. The decision is sequential because present dispatch affects future ramping capability and future operating cost. Reinforcement learning becomes useful when the dispatch problem includes nonlinear constraints, uncertainty, and repeated decisions over a horizon. The agent can learn dispatch adjustment behavior from historical or simulated scenarios. I still keep the engineering interpretation first. A dispatch policy is valuable only if it reduces cost while satisfying physical security constraints. A lower mathematical reward without feasibility is not a useful dispatch result. The economic dispatch optimization model is mapped to a multi-step Markov decision process. The optimization side minimizes total cost, including fuel cost and reserve cost, under power balance, generation limits, ramping limits, voltage limits, line flow limits, and apparent power constraints. The reinforcement learning side defines the state space, action space, and reward. The state includes load, renewable output, generator output, and possibly other operating variables over time. The action adjusts generator output or dispatch commands. The reward is designed from fuel cost, reserve cost, and total cost. The important modeling idea is that dispatch is not a one-time static calculation. If a thermal unit is dispatched aggressively at one time step, its ramping capability at the next time step changes. If renewable output changes, the reserve requirement and balancing cost also change. The multi-step MDP representation lets the agent consider these time-coupled consequences. The engineering challenge is to include enough constraints so that a learned dispatch policy remains operationally feasible. I also distinguish economic optimality from operational acceptability. A schedule with low cost but poor ramping margin, high imbalance, or hidden line overload is not a valid dispatch policy. Constraint-aware reward design is therefore part of the dispatch model. The penalty functions convert constraint violations into reward penalties. Power imbalance penalty punishes mismatch between total generation and total load. Ramping over limit penalty punishes changes that exceed generator ramp capability. Voltage over limit penalty punishes voltage outside allowable bounds. Line flow over limit penalty punishes apparent power flow above thermal limits. The total penalty function combines these terms with weighting coefficients, and the reward becomes negative when violations occur. This structure is essential because a cost-minimizing policy without penalties might reduce generation cost by ignoring security. In real dispatch, the cheapest schedule is useless if it violates line limits or cannot follow ramping requirements. The penalty design also controls learning behavior. If power imbalance has too small a penalty, the agent may accept imbalance to reduce fuel cost. If line overload penalty is too weak, the policy may create unsafe transfers. The weights therefore represent operator priorities. Reinforcement learning for dispatch must be judged by both cost and constraint satisfaction, not by reward alone. The PPO algorithm is introduced for problems where both state and action spaces are continuous. Economic dispatch fits this description because generator outputs, renewable forecasts, load levels, reserves, and voltages are continuous quantities. The page compares policy gradient, actor-critic, TRPO, and PPO. Policy gradient directly improves the policy but can be sample inefficient. Actor-critic adds a value estimate to improve learning. TRPO constrains policy updates through a trust region, but the optimization can be more complex. PPO uses a clipped objective that approximates the trust region idea in a simpler way. This makes it attractive for dispatch training. The policy can be updated using batches of time series operating data, while avoiding large jumps that destabilize the learned controller. In an operating context, smooth policy improvement is important because a dispatch policy should not suddenly shift from conservative to aggressive behavior. PPO provides a practical balance between policy flexibility, stability, and computational convenience. The architecture combines actor network updates, target actor networks, new and old policy distributions, action probability ratios, a memory bank, discount rewards, and critic network updates. The diagram is more complex than a basic PPO flow because it is connected with generative adversarial imitation learning. In imitation learning, the policy does not learn only from a handcrafted reward. It also learns by comparing generated dispatch behavior with expert or perfect dispatch behavior. The discriminator judges whether a dispatch trajectory looks like the expert trajectory, while the generator or policy tries to produce better trajectories. The actor network update uses the probability ratio between new and old policies, similar to PPO. The critic evaluates the state value and advantage. For power system dispatch, the motivation is clear. A perfect or high-quality dispatch solution can provide guidance, but solving perfect dispatch online may be too expensive. Imitation learning allows the policy to learn the structure of those solutions and generate fast dispatch actions later. This is especially useful when the expert solution contains implicit operational preferences. The imitation signal can capture smoothness, reserve allocation, and renewable following patterns that are difficult to express with one simple scalar reward. The case uses a modified IEEE 14 bus test system containing 5 thermal generating units, 1 wind farm, and 1 solar station. The network diagram shows buses, branches, generators, and renewable integration. This system is small enough for detailed algorithm testing but rich enough to include the major dispatch interactions, thermal generation cost, renewable uncertainty, load balance, and network constraints. Adding wind and solar changes the dispatch problem because renewable output is variable and partially uncertain. Thermal units must provide flexibility and reserve, while line and voltage constraints still apply. The case therefore tests whether a learning-based dispatch method can coordinate conventional generation with renewable power. The use of a standard test system is important because it allows comparison with other algorithms and with conventional optimization. The goal is not to claim that a 14-bus case is a full-scale grid. It is a controlled environment for validating the modeling chain before moving to larger systems. The dispatch case builds 5-layer fully connected neural networks for the actor and critic. The state space dimension is 21, and the action space dimension is 5. The actor network receives the operating state and outputs dispatch actions, most likely the output adjustments for thermal units. The critic network receives state information and evaluates the quality of the policy through value estimation. The hidden layer sizes show that the model is not a shallow linear rule. It can capture nonlinear relationships among load, renewable output, generator operating points, and constraints. At the same time, the network is not so large that online inference becomes slow. That balance matters for power system operation. A model must be expressive enough to approximate complex dispatch behavior, but simple enough to run reliably and explainably in an operational setting. The actor-critic architecture also fits the continuous dispatch problem because actions are not merely a small set of switch choices, they are numerical operating commands. The training curve shows reward increasing while penalty remains controlled. The blue reward curve rises with the number of trainings, and the sliding average reward becomes smoother. This indicates that the policy gradually learns a dispatch behavior that reduces operating cost while avoiding heavy penalties. The cost table compares PPO and SCOPF. Generation cost, reserve cost, total cost, and computation time are listed. PPO has a total cost close to the conventional method while achieving a much shorter computation time in the displayed case. The engineering interpretation is that a trained policy can provide very fast approximate dispatch decisions after the heavy training phase. That is valuable for repeated online or near real-time decision support. The table should be read with discipline. A fast learn method must still be checked for constraint satisfaction and robustness. But when the cost gap is small and time is much shorter, reinforcement learning becomes attractive as a fast policy approximation for dynamic dispatch. The generative adversarial network structure contains a generator network and a discriminator network. The generator produces a dispatch policy, while the discriminator evaluates whether the generated dispatch resembles the perfect dispatch strategy. The left flow includes begin, execute, analyze, examine, and rectify, which reflects an iterative operating loop. The power system state enters the generator, the dispatch action is produced, and the discriminator compares generated trajectories with reference trajectories. The update formulas show how the discriminator and generator influence one another. For economic dispatch, the method is useful because expert optimization can be used as a teacher. Instead of hand designing every reward detail, the learning system can imitate high-quality dispatch behavior. That does not remove the need for physical constraints, but it gives the policy a stronger target. The engineering value is speed. Once trained, the generator can output dispatch decisions quickly, while the discriminator-guided training has already pushed the policy toward behavior consistent with a high-quality optimization benchmark. I see this as a way to compress optimization experience into a neural policy. The offline optimizer teaches the shape of good operation, and the online policy returns decisions at inference speed. The perfect dispatch profile plots load, thermal generation, wind, and solar output over time. The time horizon contains many changes in demand and renewable generation. The thermal generation layer follows the net load after accounting for wind and solar contribution. When renewable output is higher, thermal generation can be lower. When load increases or renewable output falls, thermal units must increase output while respecting ramping and reserve requirements. This chart represents the target behavior that a learned dispatch policy should approximate. It also shows why dispatch is a temporal problem. The operator is not solving one isolated hour. The schedule must track a changing trajectory. Renewable fluctuations create repeated adjustment needs. A learning-based policy trained on many such trajectories can learn the relationship among load, renewable output, and thermal response. The visual value of the chart is that it makes the dispatch objective concrete. Meet the load curve, use renewable energy, and allocate conventional generation smoothly and economically across the horizon. The reward comparison shows deep reinforcement learning and generative adversarial learning over training. The orange curve rises quickly and reaches a high reward region earlier, while the blue curve improves more gradually. The sliding average curves make the comparison easier to see by reducing noise. This result suggests that imitation from high-quality dispatch behavior can accelerate learning. When the policy receives only a handcrafted reward, it must discover good dispatch patterns through exploration. When adversarial imitation is added, the discriminator provides an additional signal about whether the generated dispatch resembles expert behavior. That can guide the policy toward useful regions of the action space faster. In power system dispatch, faster convergence is valuable because simulation and optimization data can be expensive. The result does not mean that adversarial learning is always superior. It means that when expert dispatch examples are available, they can be used to improve training efficiency and policy quality. The final policy must still be evaluated on cost, security, and generalization. The probability density plots show the dispatch output distribution of 5 generators at 1800 on one day. Each generator has a concentrated distribution around the likely output level, but the spread and shape differ. These distributions are important because a learning-based dispatch policy can produce stochastic or scenario-dependent actions rather than one fixed deterministic schedule. The density reflects uncertainty in load, renewable output, and learned policy behavior. For an operator, the distribution helps answer a practical question: how likely is a generator to operate near a particular output level under the policy? If the density is very narrow, the policy is confident or the scenario is tightly constrained. If the density is wide, the unit may need more operating flexibility or the input uncertainty may be larger. The chart also supports risk analysis. Generator outputs should not frequently approach operating limits unless justified by system conditions. Probability density visualization therefore turns a learned dispatch policy into an interpretable operational profile. The dispatch scheme produced by generative adversarial imitation learning is plotted against the load, conventional unit output, photovoltaic output, and wind output. The conventional generation follows the residual demand after renewable generation contributes. The colored areas and curves show how the learned schedule tracks the changing load while using renewable output. The important engineering observation is whether the learned dispatch follows the shape of the load curve without excessive oscillation or unrealistic jumps. A good schedule should respond to renewable changes while respecting ramping and unit capabilities. The learned dispatch appears to reproduce the broad pattern of the perfect dispatch profile, which indicates that imitation learning has captured meaningful temporal structure. This type of chart is more informative than a single cost number. It shows whether the schedule behaves like a plausible power system dispatch over time. The method's value is strongest when it can generate such trajectories quickly for many operating scenarios while maintaining acceptable cost and security. Root mean square error measures the deviation between the proposed dispatch scheme and the perfect dispatch scheme. The formula squares the difference between predicted and reference dispatch values, averages across samples, and takes the square root. A smaller value indicates that the learned dispatch is closer to the benchmark. The table compares GAIL, PPO, and SCOPF. GAIL has the smallest displayed error and a very short computation time. PPO has a larger error but is also fast. SCOPF has the largest error in the table and longer computation time. The curve on the right shows RMSE decreasing with the number of trainings, meaning the learned dispatch becomes closer to the benchmark as training proceeds. For engineering evaluation, RMSE is useful because it quantifies trajectory accuracy rather than only final reward. It should be used together with cost, constraint violation, and robustness tests. A low error is valuable only when the schedule remains feasible and secure. I also interpret computation time as an operational metric. If a high-quality schedule can be approximated in milliseconds, the operator gains room for scenario screening, contingency review, and repeated rolling horizon updates. The final outline returns to the complete course structure. The conclusion integrates the previous applications: system restoration, transient stability control, and economic dispatch. Each application has a different physical problem, but the reinforcement learning formulation follows a common pattern. The state must represent the operating condition. The action must represent an executable control or dispatch decision. The reward must represent security, economy, restoration, and constraint satisfaction. The environment must evaluate the physical consequence of the action. The agent must learn offline from many scenarios before it is considered for online decision support. This common pattern is the main takeaway. Reinforcement learning is not a generic label attached to power system operation. It becomes useful only when the engineering problem is translated carefully into state, action, transition, and reward. The conclusion also prepares the research summary, where applications in optimal dispatch, AGC control, reactive power optimization, system restoration, and transient stability emergency control are presented as connected innovation areas. The technical innovation table organizes the research contributions by application. Optimal dispatch is connected with dynamic economic dispatch based on adversarial imitation learning. A GC control is connected with a dynamic optimization strategy based on deep reinforcement learning. Reactive power optimization is connected with a PPO-based optimization strategy. System restoration is connected with distribution network load transfer control based on deep reinforcement learning. Transient stability emergency control is connected with an emergency control decision-making method that combines deep Q network learning and transient energy function design. The table is useful because it shows that reinforcement learning is not confined to one narrow operation task. It can be adapted across dispatch, frequency control, voltage and reactive power control, restoration, and stability protection. The common contribution is the conversion of complex dynamic operating problems into learnable policies. The engineering value is faster decision support under uncertainty. The research value is the integration of power system physical models, simulation environments, reward design, and deep reinforcement learning architectures. I want students to notice the repeated pattern behind these innovations. Each result begins from a concrete bottleneck, such as real-time speed, nonlinear dynamics, topology change, or renewable uncertainty, and then selects the learning architecture that fits that bottleneck. The research results list published papers and invention patents related to reinforcement learning in power system operation. The papers cover AGC dynamic optimization based on PPO, online transient stability assessment with graph neural networks, transient stability emergency control based on deep reinforcement learning, dynamic economic dispatch based on deep reinforcement learning, reactive power optimization based on proximal policy optimization, decision-making for transient stability emergency control, and fault restoration based on graph reinforcement learning. The patent list includes emergency control, AGC dynamic optimization, load transfer, and distribution network load transfer methods. This record matters because it indicates that the ideas in the course have moved beyond isolated algorithm examples. They have been developed into multiple research outputs across operation tasks. For students, the lesson is that reinforcement learning research in power systems requires both algorithm knowledge and domain knowledge. A publishable or patentable result usually comes from matching an algorithmic capability with a real operational bottleneck, such as response speed, uncertainty, topology change, or nonlinear constraints. The course ends with a central message. Reinforcement learning can assist power system operators when the decision problem is sequential, uncertain, constrained, and too complex for simple fixed rules. In distribution restoration, the agent learns switching strategies that recover load while respecting topology and operating constraints. In emergency control, the agent learns fast corrective actions that protect transient stability while limiting control cost. In economic dispatch, the agent learns time-coupled operating policies that approximate high-quality dispatch with much faster online computation. Across all three applications, the physical model and the learning model must support each other. State variables must carry real system meaning. Actions must be executable. Rewards must penalize unsafe or uneconomic behavior. Simulation must be credible, and online use must include validation and safeguards. My final advice is to treat reinforcement learning as an engineering decision framework, not as a black box. When it is designed around grid physics and operator objectives, it can become a powerful tool for modern power system operation. I hope students remember the workflow, identify the operational bottleneck, define the state and action from physical quantities, design reward from business and security objectives, train safely in simulation, and verify the policy before online use. Thank you.